The orthonormal property of the transformation matrix A. Now, if the unprimed and primed coordinate systems are orthonormal, we have seen that we can write the transformation matrix elements Aij as Ei prime hat dot product with Ej hat. And because Ei prime hat dot product with Ei prime hat is equal to 1, this means I should be able to write Ei prime hat dot product with Aij Ei prime hat. This dot product is equal to 1, and I would find this dot product is equal to 1, Aij is equal to Aij. So that means, this implies, I can write Ej hat to be equal to Aij Ei prime hat. So with that substitution here, I obtain Ei prime hat dot Ei prime hat, which is 1, so Aij is equal to Aij. So this is what it implies. Now, if I take the dot product between Ej hat and Ek hat, so let's do that. Ej hat dot product with Ek hat, where Ej hat can be written as Aij Ei prime hat. This is the dot product with Ek hat. Since this is an orthonormal coordinate system, Ej hat dot Ek hat, this dot product we know is equal to Kronecker delta Jk, which means when J and K are equal, that dot product is equal to 1. And this is going to be Aij multiplied with, you can see here, Ei prime hat dot product with Ek hat, which is simply Aik. Aik. Now, Aij is actually Aj transpose. So that means, transpose means we have to switch the order of the indices I and j. So Aj transpose means Aij. So Aj transpose multiplied with Aik. And this is Aj transpose. Now K is a dummy index, so I can also call it J. So let's call it J. Ai J. And Aj transpose is Aij, but Aij is equal to Aj transpose. So what does this tell us? This tells us that if I take the A matrix and multiply it with its transpose, I'm getting Kronecker delta Ji. So that means this is because K has been replaced with J here. This is going to give me Kronecker delta Ji. All right. And in matrix form, this implies A matrix multiplied by its transpose, Aij, Aj transpose. This is describing for us a matrix multiplication because the indices are in the correct place. Aij, A transpose, Ji. So that's going to give us Kronecker delta Ji or Kronecker delta Ij. Now this means in matrix form we're getting the unity matrix. What is this unity matrix? It's equal to 1 when the I and J are equal. That means it's a square matrix whose diagonals are 1. So with ones on the diagonal, and every other term is 0. So it's zeros elsewhere. So this orthonormal property of the coordinate system, unprimed and primed coordinate systems are orthonormal, automatically implies a transformation matrix that takes us from one orthonormal coordinate system to another one, satisfies the property A multiplied by its A transpose is equal to the unity matrix, which is a square matrix with ones on the diagonal and zeros elsewhere. And this we have shown by looking at the matrix elements Aij, which is by definition Ei prime hat dot product with Eg hat, as we have seen before. And that means for Ej hat, I can write Aij Ei prime hat because that dot product is equal to 1. Aij must be equal to Aij. So Ej hat is Aij Ei prime hat. Ej hat dot product with Ek hat, on the other hand, because it's an orthonormal coordinate system, is Kronecker delta Jk. For Ej hat, I can replace this, and for Ei prime hat dot Ek hat, this is Aik. And so I recognize here that Aij is Aki transpose, and K can be replaced with J so that I obtain Aij Aj transpose, which is Kronecker delta Ji, and that describes for us the matrix elements of a unity matrix, which is the square matrix with ones on the diagonal and zeros elsewhere.